second day session of online FDP sponsored by the AICT Training and Learning Atal Academy on System Engineering on the topic Recent Trends and Advances in IoT here. So, on behalf of Triple IT in our fraternity as well as a FDP coordinator, I welcome you all in the second day first session here. So, this second day first session is based on the introduction to antenna system here, basically here on the topic antenna for IoT here. We will start this session after a minute. So meanwhile, before we start here, let us review the instruction here. First, during the presentation at any stage, if you find you have a query here, you can type it in the chat box here. If it is very urgent, you can unmute yourself and ask the questions here. But it is advisable to ask in the last here, or you can type in the chat here. So it will be easy for the speakers to manage through it, because if many persons start speaking, that will be difficult to manage here. So just to maintain the decorum here, we will move ahead with our conventional discussion as we have followed in yesterday's session. All the three sessions were very successful. People have cooperated very well here. So we expect this cooperation to be continued. So before we will start the technical sessions here. So this technical session will be taken here. So I am going to start this technical session third for the today's here, and this will be the session 4 on the day 2. So as a speaker of this session here, so I welcome you all again here in this online FTPs on system engineering, recent trends and advances in IoT. So in this session, we will talk about the antennas for IoTs here, and we will discuss few of the fundamental things related to the antenna, and subsequent to that we will move on some practical application related to the IoT's antennas here. So with this note, let us start here the technical session discussion here. So when you talk about the antenna system here or IoT here, then first we need to understand why we are looking for this antennas and why it is so critical in the present context here. So as we have seen in the study session, it is highlighted by many of the speakers here. The nowadays trend is uh, for the IoT devices or the connected devices is increasing exponentially here. So in by 2020, if you remember one of the stats here, so on an average here in this earth here, 6.58 devices are connected with a one user here, and this number is going to be continuously enhanced here. And we all know that antenna is a very crucial component in this journey, which plays a very vital role in the growth of any communication system here, or you can say more precisely in the transmitting the information. Antenna is the main backbone, or you can say front end of the system here. So when we see the antennas here, as we are continuously moving ahead for more and more number of devices integration on the system here. If we are willing to integrate more number of devices here, then subsequent to that, we need to also think for their possible integration with the system here. So based on the application or the shape or design of the system here, we need to go for the conformal antenna kind of structures here. The moment we see the conformal or the property which makes us for the easy to integration with the system here, put a lot of challenges to the designers here for the antenna system. So the designing the antennas for the IoT compared to the conventional antenna designers, it's very challenging here, especially if I look in the context of antennas for the 5G system here, which is also one of the enabling technology or we can say promising futures for the IoT expansion here in the upcoming futures here. If you go for the designing of antennas for the 5G system here, then you will see the complexity increase multifold here. If we keep on moving for the multiple devices integration at the one platform here, or you can say enabling a technology or designing an antenna which could work simultaneously on the multiple uh, multi-band here for the multiple IoT devices communication purpose here. It puts a lot of challenges for the designer here. The moment we move from one antenna to the multiple antenna system here. So let us start with a very brief discussion, or you can say this fundamental recalling of the antennas here, and then we will move to the our main topic of the today's discussion, antennas for IoT. Yeah. So when we define the antenna here, so there is a very conventional definition of the antenna. The antenna work as a transducer. It converts just like a transducer from one form of energy to the another form of energy here. And more precisely, or if we connect it with the antenna functionality here, then we say that antenna converts guided electromagnetic waves to the unguided electromagnetic waves here, and vice versa here. So whenever we see the guided electromagnetic waves or the unguided electromagnetic waves here, then it could be understood very easily here. If we see based on the physical connection or the way the wave travels here, or I guess information traveling here. So when we say the guided electromagnetic waves here, so those waves here being passed through the metal wire strip, or you can through the transmission line or through the coaxial cable here. If we are connected source end here, the information is traveling through those medium here. Then it is called as a guided wave here. In case of electromagnetic waves here, but once it is in open air transmission, so there are two antenna system here, and these two antenna system are transmitting here. This channel in between the two antenna system is the air here. So in case of air medium, so we can say this is unguided electromagnetic waves here. And this is the beauty of the antenna system, that they provide such kinds of functionality here, or I can say flexibility to the user, that without a wired connections, we are able to transmit the information from one place to the another place here. So this is the typical beauty of the antenna system, and that's why they are so important in any communication system here. The moment we have this wireless communication functionality with us here, a lot of system installation and putting the fibers or transmission line inside the ground or the sea here, a lot of things, a lot of functionality or a lot of cost reduction here from the operational point of view, we get advantage on those terms here. So before we move further, let us try to understand what is the basic fundamentals of the antenna, how this antenna is able to transmit from one antenna to the another antenna system here, or you can say from one antenna to the another antenna here. So this could be seen very easily if we try to look the radiation mechanism here. So whenever the antenna is capable to transmit the information from one antenna to the another antenna system here. So there were some fundamental conditions which need to be satisfied by the antenna system here. So to create the radiation, there must be primarily two conditions. So either it could be a time varying current, or there could be acceleration or de-acceleration of charges here. If either of the two condition here is satisfied, then we can say this radiation phenomena will take place. The reason is very simple. If you look at the more fundamental perspective here, then if I put a charge somewhere here, then this is the property of the charge here, that it throws the energy in its surrounding here. So when it is throwing the energy surrounding here, there's some kinds of radiation or there's a propagation of the waves here, it creates here. This is the property of the charge here. But whenever it is a time varying current here, Then what is happening? How we define the current? I is equal to dq by dt here. I is equal to dq by dt. So if there is a rate of change in the charge here, if there is a change here in the charge, then it will lead to the generation of the current here. That's why the first point is time varying current. So I is equal to dq by dt. If you need to define the current, its current is nothing but the rate of change of the charge is the current here. So with the time, if there is a change in the charge values here, then we can say it will generate a current here. So whenever the current is here, it will lead to the magnetic field presence here. Whenever the charge is here, it will lead to the electromagnetic field here. If it is time varying here, so from one another could be generated here. We will see a little bit later. Or second is acceleration or deceleration of charges. Means if there is a continuously change here, the values, or there is a movement here, velocity here, which is not constant, but it will keep on changing here, then it also leads to the radiation phenomena here. So if charge is not moving, then current is not created, there is no radiation. Even if charge is moving with a uniform velocity, so even that there is further two categories. There is no radiation if the wire is straight here and infinite in extent. There is radiation if the wire is curved here, bent, discontinuous here, terminated or truncated here. So all this is related to the constraint. So question arises here: if the charge is moving with a uniform velocity, then first case, if the wire is straight here, then there is no radiation. But whenever there is a bend here or curve here, continuities here, then there is a radiation enhancement here. Why? What happened so specifically to the these bending here? If you look at the basic structures here, so whenever there is a bend or curve here, at that time we will observe if we see if you simulated any antenna structure in any of the simulator here, here like CST, HFSS, FECO, or anyone here, which you have used here, or ADS or any other here. So if you explore the surface current part here, surface current density, then you'll observe, so as those bends and curves, if you see, there will be change in the current paths. If you can very easily verify these concepts here. So corresponding to the bends, curves, and discontinuities here, if you observe, at those points here, there will be change in the current paths. So whenever there is a change in the current paths, it will lead to the radiation here. So once there is a enhancement of the radiation here, or there is a change in the current path, it leads to the radiation here. That's why we will get the radiation whenever we are putting some kinds of curved bends or discontinuities in the design itself here. And the very beautiful example of this kind of example is a fractal antenna system here. If you type it here on the IEEE Explorer or Google here, then you will find related to the fractal antenna a ton of examples which will be explaining very beautifully and more deeply here. So once we use the fractal designs here, then a lot of additional benefits we get here. And the last condition which facilitates us in terms of radiation mechanism, if charge is oscillating in a time motion, it radiates even if the wire is straight here. So as if it is oscillating in a time motion here, so it will be time varying current here. So there will be obviously a variation here. So even if it is straight, it will lead to the radiation here. So there is a very beautiful example. You can understand this difference. If all of you have seen, when we are talking about the two parallel wire cable here or the coaxial cable here, so through the coaxial cable we never get the radiation, correct? But once we talk about the antenna system here, so we are getting radiation from the dipole antenna. But once we take the example of coaxial cable, we are not getting the radiation from both the medium here. There is a guided wave which is propagating inside the medium structure here. So what is so specific about this here? These two structures. So in one case here, if we observe, we are getting the radiation. In case of dipole antennas, in another case, we may consider the coaxial cable or parallel wire cable here, then we are not getting the radiation here. And both the structure are very much similar in the shape here. The reason is, once we are considering the two antenna system here, at that time they are very close, and the direction of current in both the parallel wire is opposite of each other. So the radiation caused by the one will be cancelled by the radiation caused by the other here. So the overall radiation is zero, as the one effect is cancelled by the another here. As we will not get any radiations here. So these are the very fundamental concepts related to the antennas radiation phenomena here. So once we talk about the radiation phenomena as well as electromagnetic waves here, this discussion could not be complete if we didn't discuss about the Maxwell equations here. So the Maxwell was the person who has given a unified theory here by combining all the fundamental properties, or you can say fundamental principles available at that time here. He unified all the fundamental laws here at the one platform and presented a unified theory, which is generally called as a Maxwell equations here. So, so if you see from all these equations here, if you look up the equation number 3 and equation number 4, so here from equation number 3, del cross is equal to minus del b by del t, and del cross h is equal to j plus del d by del t here. So the beauty of this equation is that from here you can observe that if we have the presence of one field, then the another could be generated here. Or so you can say if we have the time varying magnetic field, it will lead to the electric field generation, and if we have the time varying electric field, then it will lead to the magnetic field generation here. So as a del dot d, d is nothing but epsilon e here. So from here we can derive the expression for the electric field here. So this is all the equations is related to the time varying case here. So time varying electric field or the magnetic field which are generated here, these propagates at the speed of light here. And this is another property of these waves here. So once they strike out any surface here, or metallic surface here, actually we are talking in terms of antenna system here, the receiver perspective here. The moment these waves strike it here and the receiver end here, they induced again the electric and the voltage properties, electrical properties here in terms of voltage and the currents here. So these are the few of the basic understanding related to the antennas, and these are the fundamentals or this very popular category of the antenna system here. So dipole is the one from where the journey started here, initial days, and subsequent to that helix, which is a very popular application for the space applications here. So if you go with the space applications, we will talk a lot about the helix antenna due to their special properties, which is not present in another antenna systems here. Along with this pyramidal horn, rectangular patch antenna, rectangular waveguides. So there is a lot of functionality here, or varieties in the antenna system here based on the application we use it. Then Yagi-Uda array antennas is very one of the original research in case of antennas here. If you go through the IEEE proceeding here in the 19th centuries, when the people, Professor Yagi and Professor Uda has invented this work here. I think it was 1960 or something, if I remember correctly here. So it was it is considered one of the genuine invention by the IEEE also here. And these are the very few papers in the IEEE proceedings here where they have replicated or produced the original work later on again here. And Professor Yagi Uda's work is one of them here. So if you see, go through the history of this Yagi Uda antenna, you will find a lot of more interesting stuff here. Okay, but this is not the time for us to go in the detail of those things here. So apertures array, this is another kind of antennas, microstrip patch array, parabolic reflector with fronted, parabolic reflector with Cassegrain feed here. So DTH applications we are using these kinds of antennas here. We are using the parabolic reflector kind of structures to receive the electromagnetic waves from the space, and we are receiving the signals at our home. So if you need to define the characteristic of the antenna or the functioning of the antenna here, then these are the few important parameters. And based on these parameters, we used to characterize the antenna functionality here. The radiation pattern, radiation power density here. So how the antenna is transmitting the power in its surrounding, those things could be articulated or find out here as parameter input impedance here. So through that we could find out how the antenna is transmitting within a range of frequencies here, and what are the proper impedance matching proper impedance of those systems here within that band here could you find out. As we all know that if the impedance matching is not properly, then in that case the losses reflection will be taking place here. If you remember, reflection is equal to gamma is equal to ZL minus Z naught divided by the ZL plus Z naught, where ZL is the external impedance here and Z naught is the impedance system here. So what are the external we are keeping? So this ZL need to be perfectly matched with the Z naught here to avoid any kinds of reflections here. If this input impedance property is not taken care in the design, then it will lead to the reflections. What will happen when you are going for the feeding purpose here? At that time, a lot of feed or the powers here, feed power here will be reflected here, or will lead to the losses. Means the heating and other things will take place here. It may damage your systems here. Once you have done all these parts, then efficiency, gain, and the bandwidth here. So how efficient the antenna system in design itself is here in terms of transmission of what is the power we have provided in the system for the transmission, or you can say what is the efficiency of the antenna system to transmit effectively the guided wave to the unguided wave here, or you can say from the voltage or current to the electromagnetic wave in terms of electric field and the magnetic fields here. So those things we could always look based on these parameters. It's a discussions here. And the last, which is bandwidth. So what is the operating frequency we are considering? We are talking about the narrow band antenna. We are talking about the wide band antenna systems here. So based on that, a lot of trade-off in terms of all these parameters efficiency will be present here. So now we will try to connect with our antenna systems here with promising applications of IoT versus talk, which is talked a lot nowadays here. So as we were discussing in the previous class too here, so when you talk about the IoTs here, so IoT is nothing but the internet working of physical virtual devices for the collection and transfer of data here. So when we say the physical or virtual devices here, so physical or virtual, if you remember, so we have discussed in the previous session here, there's a lot of functionality could be there, or times will be there here from any sensors here or virtual devices from the data social platforms here, we could take it here, correct? So in terms of their physical here, this our healthcare system data layer, like our body weight, our temperature, our heart rate, our ECG here. So our glucose level in the body here. So a lot of information could be collected. So all these things are part of this physical and virtual here. Information through the social network here, WWE platforms here. So all the integration of these things will be under the broader umbrella of IoTs here. So what are the parameters which is facilitating such kinds of growth here? We are expecting for the interconnections of all such kinds of devices, or you can say healthcare, agriculture, smart banking, or everyone will be integrated here. So all the information will be available to access from anywhere in the world here. So these are the parameters which facilitate a lot here for the current exponential growth in the IoT system here. So and this growth in IoT is generally driven by the parameters ubiquitous use of the internet here, as we can see in our country also here, from we see from the last 1 decade here. So what are the scenario in 2010 here now compared to that with the 2020 present here? We see the use of the internet have been increased exponentially here. with a few new service provider as well as the change in the rules and regulation by the TRI here. So there is a tremendous increment in the use of the internet here. Here you can observe it. This is also based on the continued build out of wireless network, operational efficiencies often through the data management, increased functionality for safety and securities, increase in the computing capacity here. A lot of cloud related services are present to us. From the hardware perspective, we see a lot of new advanced hardwares are coming here. So you can see compared to the if you see the 10 years ago mobile phones here. Now if you see with the present one here. So you can see this kind of mini computer. A lot of functionality is present here. So 4 GB, 6 GB RAM with RAM, your mobiles are coming here. Here which are they have 64, 128, 256 GB kind some memory card is already there. They are putting the graphics card here. Advanced camera system is also there here. So a lot of computational functionalities provided here as well. If you see in customer mobile here, you can see if you're playing some game, if you're on the auto rotate and other things here. So a lot of sensors are also inbuilt it here. The moment you touch it here, there will be a light on the screen here. If you make a movement here, they will automatically sense here. Like if there is idle situation like this, the moment you touch it here, press a key here, you will see that this is on here. So how these things are happening? Because a lot of functionality or sensors is integrated here. If you open your GPS system here, you can see how it is presenting accurately north and south directions here. This is all possible here because some kinds of inbuilt functionality we have created here, or a computing capacity is inbuilt here as here, but at the same time keeping the power consumption level very slow here. Because what is the function? What are the functionality I am getting here? We have to pay in terms of corresponding price here in the other segments here. We didn't want a mobile system here, which is with us here for a 4 hour or 2 hours. So backup here. I need to recharge it after every 2 hours, 4 hours here. It's power level. The moment you charge it, its power level is fixed here. So we need to go for optimized usage here. If you keep the mobile phone here, if it is idle for the few minutes here, 2 seconds here, it will be automatically off here. It will go to the idle mode here. Here. Simultaneously, it is continuously having the connections with the nearby the BTS tower here. So some communications here it is continuously taking place here. So that BTS is also aware that how many active devices are present in the surrounding here, how many mobile phones are active. Out of that, even though how many of these are in the active mode, I mean, how many mobile phones are as present are busy in the conversation mode here. So those things would be very much identified based on the monitoring the power level of associated devices here. But once the mobile phone in the idle mode here, their power level is a different stage. If the moment we're going to go for the audio call or video call here, at the time the power consumption is more here. Or if we are going for some graphics or the video game here, even in those cases, the power consumption is more here because we are going for some types of you can say computational part here. So comes some computational functionality we are utilizing in those operations here. That's why we are losing the battery power here. So those all this functionality which is enhanced within the last 1 decade or 2 decades here in the mobile communications here. These are the main key parameters here which facilitate us with such a growth here. So if you see precisely here, IoTs and the antenna technologies here, so we can say antennas allows users to gain remote access to their device of choice here, eliminating the need for direct wiring between transmitting and receiving devices here. So once we are going to retrieve the information from some places here, we have to connect it through the wire each and every time here. And one very beautiful example is if here through the Wi-Fi. I can connect a lot of sensor devices to the Wi-Fi, but it doesn't mean we need to connect it with the wire here. For example, I can connect my mobile phones here, and the mobile phones a lot of sensors here are available here. So I could integrate them, or in the home appliances I could integrate my Wi-Fi or through my phone here. but it doesn't mean they need to be integrated with directly with my phone or the Wi-Fi here. This could be a wireless mode connections here. So these functionalities is available to the end users here because we have the antenna at one end, and this is the job of the antenna here to facilitate our life here, where we can design the system based on the application requirement, which will take care of the communication part here, or to facilitate wireless medium of transmission of information here. So at any place I can move here. If I one beautiful example you can understood here. Nowadays we talk about the mobile phones here, but just see the scenarios of 2 decades ago here. At then people will have the landline phones here. In case of landline, if you know, there was a proper connection of the wired here from in end user into unit. There's a proper wired connections here. You don't have the flexibility to move with the telephone into the other places here. That's a fixed location. If we want to talk or listen something or have a discussion here, then we have to go to that place here, and then we have to initiate the discussion or conversations here. So there was a restriction in terms of movement associated, and there was a location specific here. But now, with the help of mobile phones here, I can move to any other places here, and I can enjoy the degree of freedoms here, and I can enjoy the service here with the proper moment here. So based on that, if I categorize the antennas here in the context of IoT applications here, then there are mainly four broader categories here, and these broader categories is related with embedded antennas, internal cable antennas, outdoor antennas, and external antennas here. Okay, I think some questions was coming. So one question is coming from Suma V Setti. So do you have any questions? You can ask. Nope. Anyone have any question till this point?
Hello. Namaskar, sir. This is Sandeep from Bits Pilani.
Oh, namaskar, Sandeep. How are you?
Namaskar, sir. Please,
Please tell.
sir, please let me know the difference between embedded antennas and the internal cable antennas.
Okay.
Thank
So
you,
when we
sir.
were
Yes, sir.
so when we were talking about the embedded antenna systems here, so these are already integrated in the part here. So they are part of this design, like RFIC antenna systems here. So these antennas are directly integrated with the IC part here. So you cannot remove them here. Correct. As well as their feeding is also with the through the that board here. So if you try to look at the board here, you can see there are some kinds of connection taking out here. So these are working generally antenna systems here, and the feeding part is also managed through that IC or through that PCB board itself here. But when you talk about the internal cable antenna systems here, in case of internal cable antenna system, where transmitter or antenna could be at the one place, and through the wired connections here, or against through the cable here, we are providing them a feeding mechanism here. So this is the basic difference in terms of these two here. But as a fundamental antenna, they also will be working modes here. Correct? I hope I have clarified your doubt.
Yes, sir. Perfect. Thank you, sir.
Okay, thank you. Okay, so no query from other participants here. So let us move. Okay.
Hello. Sir, good morning.
Good morning.
Sir, myself Nipun Mishra from GGB Bilaspur.
Okay, good morning, Mr. Ji. How are you?
Sir, fine. Sir,
So please tell me.
sir, my question is, what will be the operating frequency for the IoT devices? On which frequency we have to design the antenna?
Okay, so that was the question. Actually, it will come a little bit later here. So those are parts are not going to be started. Okay, so let us give me the answer for this question here. So when you talk about the IoT devices here, then as we all know that the frequency is not free. there's always a licensed band and unlicensed band here. So we can design the IoT based antenna system in the especially ISM band here. If you see the current government norms here, so if you see there is a ISM band in the 400 to 500 megahertz band here, then previous GSM band of 900 megahertz band is again allocated as a ISM band here, especially for the IoT applications here. So if you go to literature, you will find that Indian government is especially putting the emphasis for such kinds of IoT application here, and they have dedicated this 900 megahertz of the previous GSM band here for the IoT applications here. Along with that, you can any other ISM band you can use it for the IoT applications here. There's no doubt it. But along with that, when you're designing something with a very low power here, then you can move on. But you have to be very restrictive in terms of the power level. Otherwise, it will create the conflict of interest here. So you need to be careful in terms of when you're designing the antennas here. The people generally people are used some other bands of frequency for the operation because many devices now are integrated with our mobile phones here. A lot of sensors are going to be integrated with the mobile phones here. So the people when you talk about the IoT antenna systems here, they try to club it this frequency here with this mobile functionality for Wi-Fi, WiMAX here, 3G, 4G bands here. So if you go to the literature, you will find different kinds of works here targeting these different aspects of the design application here. Here. So
Okay, sir. Thank you. Thank
okay.
you.
Okay.
Thank you.
Okay. Any other questions, or should we move on? I think someone need to unmute his mic here. Okay.
झुम्मा 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 अधर मधुर
Someone need to take care of their mic here. This is D. Venkata Siva Prasad. You are requested to unmute your mic. D. Venkata Siva Prasad. Okay. I think the issue has been sorted out. Okay, let us move on for the further discussion. Okay, so as we discussed, we can categorize in the main four broader applications here. So these categories are based on the application orientation, how we are using these antennas here. Based on that, we have categorized them as embedded antennas, internal cabled antennas, outdoor antennas here, as well as the external antenna systems here. Here. So the name as well as the figures are self-explanatory here. So let us move on the more important design related parameters. So first is antenna design influencing parameters. So we are going to discuss few of the parameters which plays a key role in terms of designing of the antenna systems here. So we'll try to look at one by one here. So before we go start here, let me clarify it here. So these are the not the mandatory parameters here. You have to check the design based on these parameters. But when we are going to design antenna system here, at that time we have to keep a note of these parameters here because these are the important parameters related to the application requirement here. So you have to be aware about what kind of application you're designing, and these parameters help us in the perfection of your design here. So let us move with the first parameter here, that is the wireless decision here. So when you talk about the wireless decision here, so later the antenna systems here, how much data must be sent, what is the data rate we are transmitting, up to what range we are looking to transmit the informations here. So corresponding these to what kind of frequency, at what range of frequency I am willing to transmit here. here, and what is the available power limit to us here. For example, if I talk about the UWB devices power level here, so in terms of UWB, it is very low, a low level, or you can say it is at the floor of the noise level here. But when you talk about the GSM, Wi-Fi, or other WiMAX here, then in those cases the power level is very much high here. So what is the availability of power to us here? So based on that, I need to take a call related to the antenna design here. So if we see, there is a wireless protocols which are linked with this here. So these protocols varies with applications to the another applications here. And based on this application, you can observe here there are some near range, low range devices here, medium range, as well as the high range devices here. And the protocols is also differ a lot with respect to the applications here. For example, if I take the Wi-Fi as well as the Bluetooth, both here, so both operating in the same range of frequency, 2.4 gigahertz. But if we look corresponding to these to the operating principle here, or the protocols which they use here in the transmission, both are different here. They are not same exactly. Same mechanism is not used for the transmission purpose here. And these protocols, if you remember, when you talk about the communication protocols, you emphasize also like the communication protocols are the main against the protocols which establish the connection between the two devices here. Just like we, as a human, we want to communicate between the two persons here. We want to establish communication between two persons here. Then both need to speak the same language here. If I'm speaking Hindi, then other person need to be also able to understand the Hindi. It doesn't mean if the person does not know the Hindi. If he is, I'm speaking Hindi, he is speaking English or French or any other language here, then it will be very difficult for both of us to communicate here. The same way in terms of devices, they are associated with the protocols here. So what protocols we are looking here. So based on that protocols, there will be a specific data transmission requirement here. So based on this data requirements, we are looking for the low data rate or high data rate here. So based on that, I need to look at the other parameters here. For example, as we all know that if we try to correlate it with the Shannon's law here. So in case of Shannon's law, channel capacity is equal to B into log 1 plus SNR here. So from that derivation, we could always take the two important conclusion. One is if I am interested to increase the channel capacity, then either way is to increase the bandwidth or I increase the SNR level here. So if I am looking for a higher data rate here or the higher range of communications here, then either of the two way I need to select here. For example, if I select the bandwidth here, then corresponding to the bandwidth, because it is linked with the protocol, based on the protocol's requirement, I need a higher bandwidth here. So corresponding to the higher bandwidth, now I need to go for a antenna design which will accommodate a wider bandwidth here. If I'm looking for the low data rates here, then I can go with the narrowband antenna systems here. So there's no universal kind of solutions here based on that here. But it doesn't mean that antenna is directly governed by the wireless protocols. Suppose if I design an antenna here for the 2 to 2 at the 2.4 gigahertz here, it is work well from the 2.3 to 2.5 gigahertz. It would work for the Bluetooth, Wi-Fi here. There's no issue here. There's no issue at all. It can work for all the three mode of communications here. So this is totally frequency independent here, protocol independent here. But in case of indirect way, this protocol is governing my antenna design. When I'm looking for the higher data rate here, if the SNR constraint is there, then I need to go for the wider bandwidth here. So for wider bandwidth, I need to go for the antenna system design, which is for the wider bandwidth here. Now, simultaneously, for remote devices, if a very long range devices I'm looking for voltage, then I need to go for the higher power also here, because a low power signal will not travel a larger distance here. So I need to take a note from there. So range is also one parameter here. So I'm looking for long range wireless protocol or medium range protocol or short range. wireless protocols here. So for the medium millimeter to kilometer, 100 meters, or less than a 1 meter here. For example, in case of your RFID tags here. So there is a small antenna system which is placed here. Just you need to click it here, or an NFC, near field communication. We need to just tap it. Just through the tapping, we want to have the communications here. So your cards here. So the one example, correct? So where we are looking for the very low range communications here. So when you are going for these kinds of applications here, then again, what is the amount of power I'm looking here? Because based on that power, what are the frequency band I'm looking here? Because if I'm looking for the longer range communications here, then it's the optimized power. Here I can move on with the low frequency applications. But if I go to the high power here, then obviously the range is going to be trade-off here. So we could understood very easily with if I take the two examples here. The one example is related to the your if I see the DTH application here, TV application where we on transmit generally at 900 megahertz as well as the 2 gigahertz range also here, 1.5 also here. So when you talk about the DTH applications here, all of you noticed whenever there is a rainy seasons. In case of rainy seasons, our communication is highly disturbed. You get a message here. There is some disturbance near to your set-top box. Kindly remove it here. What that mean here? First, the transmission or the communication through the satellite is continuously coming out here, and your set-top box is again in the same positions. Your set-top box is here. This is a mobile satellite. This is communication taking place here. But in the middle, what is happening? There is a cloud. So due to this cloud, what is happening? They at those wavelengths here, those frequencies, wavelength is equivalent to the dimension of the those drop of the water here in the rainy seasons here. What will happen? Those droplet will absorb those wavelengths here. So as the outcome of that, your transmission or the reception of your DTH will not be able to receive enough signal strength here so that it could transmit the information correctly to the TV screen here. This is the one example related to the range here. But at the same time, if you open your radio here, because nowadays very few people are using it here, but if you open the radio systems here, even in the radio system, if you observe it in terms of FM radio or radio system where we can listen the Ved Bharati or the BBC news channels here. If you see in case of BBC or news channels here, they are transmitting at the very low frequency kilohertz range here. And these kilohertz range here, the transmission is taking place from the Delhi here, and at across all the country, we are able to listen to the program here. But once we move to the FM radios here, megahertz frequency here, megahertz frequency 90, 100, there are different FM radios here. FM radios here were corresponding to the same Delhi. Delhi FM you cannot be able to listen by sitting in the Raipur, Varanasi, Ahmedabad here, correct? Or Hyderabad or Bangalore here. You cannot listen it. Delhi station. It's a program here. But the Ved Bharati program, which is broadcast to the Delhi, you can listen by sitting all over the places here across India. So what is that here? The reason is because once you talk about the low frequency communications here, and the low frequency communication, they propagate across the earth structures here. That's why their losses associated to those transmission is very low, and they are able to travel a longer distance here. But the moment we keep on moving to the higher frequencies here, their wavelength started to become comparable to the many objects in the surrounding here. So they are highly likely that they are going to be absorbed those wavelengths by some of the objects in nearby surrounding it. That's why the losses associated to the higher frequencies keep on increasing here. So when you're going to the higher frequency, we need to be selective in terms of what frequency range I am going to target it for my applications here. Because for the moment I select the frequency range here, I have to see the trade-off in terms of range here also. If I'm still looking for the same range here, then I need to go for the high frequency. At high frequency, I need to go with the high power here for the transmission purpose here. But we all know that government doesn't allow to go for the very high amount of high power transmission, because if we cross the threshold here, then it will affect very adversely to the our body systems here. Yeah, so this will be a very hazardous effect on our body here. So there is a power constraint also there. So in the design of the inter system, based on all this trade-off, you need to take a note. So data rate here based on the speed. I am looking for 1 Bps transmission, or I'm looking for the 1 Gbps transmission here. I'm looking for higher data rates. I'm looking at the higher frequency. I'm looking for the high power here. So based on the application protocols and other things, I need to take a note here. So again, you can see these are the some of the application based on the frequency where people are using here. At the very low frequency, you can say the central part, you can see there's a radio applications here people are using. Then remote control, cell phone, TV applications, 500 megahertz. Then GPS application. This nowadays is not nowadays near to this GPS is your IoT band is also have been placed here. Set 2.4 gigahertz, Wi-Fi, Bluetooth, microwave oven, pages, satellite, cordless phones, walkie-talkies. A lot of application in this ISM band have been placed here. The reason is if we go to the higher frequency, there is a one biggest advantage is if you go to the higher frequency, is that their antenna size is reduced because lambda is proportional to 1 by 1 by frequency here. So you can see inversely proportions here. If I keep on increasing the frequency, then the wavelength size is decreases, and the length of the antenna is proportional to the wavelength here. So the moment is it is keep on decreasing the wavelength here, so antenna size will be also keep on decreasing here. So at the 2.4 gigahertz compared to the ISM band, if I am looking for ISM band at the 400 megahertz here, and if I look at the other application ISM band at 2.4 gigahertz here, then at the 400.4 gigahertz, I need to design a larger antenna structure, because the moment I move to 2.4 gigahertz, it could be sorted out with a small design here. So these kinds of flexibility will observe at the high frequency, and at the high frequency we have the more bandwidth availability here. So designing a wideband antenna at the higher frequency is little bit easy task compared to designing a wideband antenna at the lower frequency here. So once you go to the design, you have to face these kinds of challenges here. So it will always trade off. That's why if you see a lot of local application or wireless personal area network application have been placed in case of 2.4 gigahertz ISM band. Even the fact we already have some additional ISM bands available in the lower frequency bands. At the 2.4 gigahertz, we get some optimized dimension of the antenna, which could be placed here with your system, this kind of system here, where with those antenna we can move on. Also, flexibility to moving those antenna will be a little bit easy here. But if you see our radio station antennas here, so very long tail here. If someone asks you to move with that kind of antenna system, it will be too difficult here. But nowadays, if a 2.4 gigahertz Wi-Fi router or like mobile phone, you can move on very easily here. So this kind of flexibility is available to us with the frequency selections here. So these are the protocols and their associated powers level here. So you can see one point here, as we are moving ahead on this graph here with the frequency. So the amount of power is also keep on increasing in order to match up the range of transmission here. So for example, starting the 8 kilohertz range here, we are transmitting with the nanowatt power here. Then RFID level hearing aid here, or you can say healthcare aid application, we are transmitting in the microwatt level here. Then for the personal area communications here, we are moved to the milliwatt here. Then for the GSM and other applications, we are transmitting at the watt level of power here. So now we can think here how many multifold enhancement in the power scale here when we are keep on moving ahead with the power here, with the advancement in the frequency here. Because if I use the same level of power at the higher frequency here, then the range will be drastically very low here. So that is not our objective here. So we don't have any other choice in place of increasing the power level here to match up the range requirement fulfill here. So these are the few of the facts here which you already discussed. So wireless protocols and antennas here. So the question comes arises here where the frequency is same here. So why can't we use the one application? Why we need to go for these three different kinds of applications when we have the all the same system working at the same frequency 2.4 gigahertz here. So the outer stays here, outer layer if I see, then it seems reasonable questions here. But if we go for the insights here based on the protocols here as well as the functionality here, so the data speed or data rate they match up is totally different here. And so their range is also different here as well as based on that application. There if you see the power consumption is also totally different with respect to each other here. So these couldn't be replaced with one, but there could be one possibility out of all the application, one antenna system could be enough to support all these three kinds of applications here. Okay. So as we have discussed earlier too, antenna system doesn't depend on the wireless protocols here directly here. Antenna work across a different set of frequency bandwidth. So if it is the same range of bandwidth here, then it is fine. It will work here. If the functionality is also same in nature, because within a band, if some kinds of application we are looking for a line of sight communication, and there is a band of certain application we are looking for omnidirectional kind of behavior here. Then in these two cases, I need to be distinct here in terms of antenna applications here. So other factors which influence antenna design, here's frequency needed for communications here. So patterns, shapes are designed to match a specific frequency or the communications here. Means as we discussed, if I am looking for the antenna system to transmit uniformly in the direction. For example, if I see the Wi-Fi applications here, in case of Wi-Fi application, one Wi-Fi router is placed at one place, and its job is to have a connection with either its present in the surrounding here. So if I'm designing antenna for the Wi-Fi application here, then I need to here so corresponding to the Wi-Fi applications here I'm designing. Then I need to design antenna system here which will be have omnidirectional behavior in a plane. The user could be placed at any other positions here. It will be very easily connected here. So they will have the chances to interact with each other here. Or information or the data could be transferred from one place to another very easily here. This way they could work on here. Similarly, the other factors, one is related to the operational behavior. So what kind of application orientation or application requirement I need to always look here. I cannot design, okay, this is 2.4 gigahertz, I have designed, so it will work. No. So you need to check its behavior. The moment I'm designing omnidirectional antennas, even I'm designing very directional focused antennas here. So this is totally different here. For example, people used to design here in case of L band, S band here for the radar systems here they were designing. In case of radar system, you will be surprised to know that they are designing very pencil beam. So hardly 2 degree, 3 degree, 4 degree, there will be order of their beam here. And so that 4 degree, 5 degree beam scanning beam range here, they will be able to transmit the power to the 1,000 kilometer ahead. And within 1,000 kilometer range here, they could scan within this beam here. Because whatever the 3 kilometer 5 degree beam here at the initial stage here, if we see it is 1,000 kilometer ahead, so that 5 degree beam will be covering a very larger cross section area at 1,000 kilometer here. So any object which will be coming in that area will be identified very easily here. So that's why, but at the same times, with the power requirement, those narrow beams for radar application antenna will be totally different here. I cannot use those antenna for my Wi-Fi applications here or for the microwave oven purpose here or the cordless phones here. So no, this application is totally different, even though are working in the same band of frequencies here. Correct. So this is the requirement here, application requirement. I need to take a note of that one here. At the same time, at what location I need to fix the antenna system here. And for example, if I am looking antennas 2.4 gigahertz, so within a mobile phone there is a Wi-Fi 2.4 gigahertz, and there is a Wi-Fi router also. If you see, there is a different antennas. If you have seen, there's a dipole antenna kind of structures coming out of that Wi-Fi router here. So both the antennas are working at the 2.4 gigahertz, but their uh, nature is totally different. The reason is because based on their placing at the system here, I cannot use that Wi-Fi antenna system with my mobile phone, or my mobile phone antenna with the Wi-Fi adapter here. So again, the takeaway from this one, this example says again at the same frequency we are working, but we have to be selective in terms of those application requirement here, because what are the shape I am, what are the places I am putting those antennas here, based on that antenna need to be designed here. So these are location specific antenna system. That's why I categorized in the 4 product categories here at the starting of this discussion here. So location of the antenna, embedded, external, outdoor conditions here, which need to be taken care. So customer use condition here. So what are the customer specific requirement related to the application? Those need to be also taken care here. In when you're designing a system, you're looking for the optimal performance here. So antenna technologies for IoTs. So the antenna development and manufacturing in the mobile industry is based on the collected experience and developed known. Means what kind of work have been already done here, and subsequent to that, what is the amount of your experience here? In case of intent design, the more you design here, the more you learn, because the more the kind of problem you face here, and subsequent to that, your learning experience will also enhanced here. So this is a very something which you learn with the experience here. Because once you go design anything, a lot of queries or problem you face here is solved with. So these kinds of learning will help you in the better betterment of design here in the next iterations here. When you go target the any next application here, at that time you will be having better uh, here perspective or better knowledge with you to design it here. So when you're going to design an antenna system here, so these are the few of the challenges here. So what kind of application I'm targeting here? I'm looking at embedded design system here, or a handheld design system here, or you can say wearable kind of antenna system here, or you can say quad band antenna system with the 4G mobile phones. I am looking at antennas here, where I'm Wi-Fi, Bluetooth, GPS, WCDMA, or means I'm looking for the customization of all different kinds of applications here at one platform here. So the moment is the one platform, there's the multi-band kind of phenomena. People look here from the same antenna system, whereas the space constraint is there. If you can design the one antenna for one specific band, you will always get the better performance. The moment you will go for the one antenna with the multi-band antenna system here, then we always there will be some kinds of trade-off in terms of their characteristic as well as the performance here. If you compare all their parameters here, then you can find out these differences very easily here. So especially when you are looking for the IoT applications here. So in case of IoT applications here, based on their diversified nature here. So their diversity, there are a lot of application we are trying to target in case of IoT here. So when you talk about the IoT applications here, then the road compatibility need to be there here. Because at one end you are getting the data from the one level of frequency here based on the source nature here. Then subsequent to that, we have to need to be compatible enough to transmit that information to the base station here. So there you need to be another range of antenna here, or another band incorporation in the system itself, so that you can transmit it. So these kinds of multi-band functionality need to be present there. So services required for such kinds of applications to fulfill here. There will be concept and scope developed here. There's electrical mechanical design expertise for the application within the allocated space here. You can fit the antenna design systems here, as well as what is the prototype you are proposing, and that need to be perfectly functioning within that allocated space here. Here, as well as the validation, as well as the compliance with experience here. So what you're designing, it need to be working with all the conditions here. For example, if you're designing something, its co-pole performance is good here, but you're not taking care of the cross-pole performance here. So it will not look good here. So cross-pole need to be also taken care here when you are looking for a long, sustainable or efficient transmission here. So EMI or EMC or everything is perfect here, but your impedance matching part is not taken care. So what will happen? A lot of losses will be taking place here. So anyone have any query?
प्रतिभा में चेक करो अटेंडेंस
Okay. So participants again requested here to take care their voice control here. You need to unmute it when you are connected to the webinar here. So now we are going to discuss few of the project applications based on the antennas for the IoTs here, where a few range of frequencies have been targeted. So whatever we have talked up to this stage here, this is related to the application requirement here. So what kinds of parameter here I need to take care when I'm looking for a specific design the antennas for the IoT applications here. Now based on those consideration or those learning here, I am looking forward to deploy those understanding or those learning here to some of the possible applications here. So the first example I am demonstrating here related to the frequency reconfigurable multiband antenna for microwave sensors here. So in this case, they have designed the antennas here for the multiband applications here. So where we have targeted from 1.7 to 2.15 to 0.13 to 3.0, 2.17 to 3.43 here, and so on. So multiple bands they have targeted here, and based on multiple bands here, they have incorporated uh, deformation in the design here, and subsequent to that they were able to get these desired bands here with a reasonable performance here. So their idea is they have a multi-band functionality in the perspective that they will have the wireless sensing, space, and IoT applications. Those things they can tackle here. So through these kinds of antenna design. There is one more Recon TTC enabled frequency tunable inverted F antenna for IoT applications here. So in this case, if you see a design here, this inverted F antenna they have placed, but along with that, what they have done, they have used digitally tunable capacitors here. So what they are doing in this work here, so through that capacitors, they are changing the voltage. As we all know, if you see the operating frequency F is proportional to the 1 upon root LC here. If I change the capacitor values by some instant here, or by some mechanism here, then this changing in the capacitor will affect the overall operating frequencies here. So here in the design, they are changing the capacitor's value, and by changing this capacitor's value, they are able to obtain a tunability in the functioning here. So it's by changing the capacitor's values here. So this way they are obtaining a reconfigurability in the functionality. So electrically small loop antennas here they are using standing on a compact ground. The one applications they are trying here. So within that a small they have proposed it for a ISM band here. So within the ISM band here they are using some diode kind of applications here through the diode or inductor section here. Here you can see at the 1 hour They are using inductor here at this side and capacitor at this side here. So based on their on and off functionality here, they are changing the value of inductor and the capacitor in the design, and based on that they are changing their operating range here. But in this case, you can observe this functionality is not too high, from 4.25 to the 0.425 to 0.44, within that range, or you can just say a range of 200 megahertz. They are keeping a shift here. So this is a design at one of the ISM band here, industrial, scientific, and medical band here, a design. And the author's objective was in this work to go for a compact dimensions here, and they have used a dimension of 18 cross 18 cross 12 millimeters cube here. So this could be the one of the possible applications where people can explore it here. And there's one more applications here regarding the IoT applications here, where they have targeted the GSM 900 and GSM 1800 bands here. So their objective in these bugs here, because what are the sensor they are integrating, they need to transfer it next over to the GSM bands here for the further communications here. So they have designed the entire system which have the proper compatibility with GSM bands here. At the same times, to keep a note of futuristic IoT applications here, they keep the design dimensions compact here, so that in case of future, if integration is required, they could go very easily for that. This is another very promising application here related to the IoT part here, and here you can so here you can see they have designed for IoT linked integrated NFC and the dual band antennas here through the RFID reader systems here. So in this case, the antenna is working at the 920 925, this is 900 megahertz, as well as the 2.4 gigahertz, this is the Wi-Fi range here, so the Wi-Fi readers here. Yes, so here the objective is for the short range communication as well as the nearby devices integration here. And this part could be done very easily. So antennas, if you see this demo printing, pictorial presentations here. So one NFC module is used here, using through the 900 megahertz part applications here, and the rest of the part will be here for collecting the data here, and this collection of data will be further communicated to the cloud services here. So for that part, they have integrated the 2.45 gigahertz range here. So this is one of the possible applications people are looking ahead in the near futures here. So where through the mobile phone communications, so through the mobile, lot of communication could be performed here. The data then, so based on that, if you see, there are two operating range here. They are showing, and one is a 900 megahertz, and another is 2.4 gigahertz here. This is another antenna systems here, where we talk about the compact planar multi-standard MIMO antenna for IoT applications here. So here objective is little bit modified here as compared to the previous cases where we're designing the antenna system here for the different bands here. But now in this case, what they have thought, in place of designing single antenna system here, when they moved here, so they have fused two antenna system in design. So there will be one wide band antenna here for the sensing purpose of the complete band here. So within that band, what are the free bands here? So maybe some of you are aware about the cognitive radio concepts here. So the cognitive radio concepts, the primary user's presence needs to be identified in the first place, and then whenever the band is not utilized by the primary user or the licensed user here, then secondary user can transmit the information in those bands here. So keeping those kinds of application in mind, this work have been proposed here. So where the first task is to what within that operating bands here. So they will sense, okay, this bands at present it is being utilized or it is unutilized here. The moment it is unutilized here, so based on through the help of other antennas here, four antennas which have been placed here, through those inter-system transmission could take place here. So this is the task. So this is the task here which have been targeted through this work here. This is one of the application nowadays from the current perspective. As we can see, people are moving ahead from the normal one antenna system to the new antenna systems here to increase the quality of services here. These kinds of applications are very much promising here to explore it further. And this application is very interesting here as well as thrilling based on the application perspective here. If you see, so here in this case, a handband zipper antennas for body-centric wireless communication IoT is here is designed here. So the authors proposed antenna system which is metallic in the nature here. It is cloned with the shape of the chip of the bag here. So you can see the dipoles are placed here just like the chip systems here. So all of them will be working for the communication purpose here. And the other dimension of the structure which have been incorporated here is very much similar to that chip systems here. So within that, as we all know, that when you're talking about the bag system here, it is not mandatory that bag is always closed here or it is always open here. So it could be multiple positions where the chip could be placed for the chip here. Right? Once you're talking about the fully closed or half closed here or totally open, then all the stages, its functionality have been verified here. And the important point is to take away is here. This bag will be placed near to our body here. So those kinds of performance is the additional things which need to be done also here. So these kind of applications are very useful, or you can say from the futuristic application requirement perspective. If I look at these things here, then these solution will be very promising. That is scale because they are very much familiar, very much connected with your daily-to-daily devices, systems which you are using here. At the same time, these kinds of devices will be gathering the information into our body here or personal health care information here. They will be communicating to the base station here for further analysis purpose here. So before we summarize this session here, let us discuss few of the research problems which are possible in case of antennas for IoTs here. And after this session, we will close the session. Yeah. So there are the few research problems related to this systems data optimization and dimension. As we are moving from the multiple IoT devices integration into one platform here. So the optimization is one thing, or the miniaturization is one thing which will be always desired, irrespective of all the you can say applications here. Whatever the application I am talking here, this is the design. This is the parameter which is always desired here. If you can reduce the dimension here, keeping the functionality at a level which is acceptable here, people will welcome it. Again, is mutual coupling reduction in MIMO antenna systems here. This is another constraint. As when you go for the multiple antenna systems here, at that time their field interaction will take place here. So how we can minimize these interactions here? Next, reconfigurability and functionality in terms of bandwidth. We already seen here. In terms of polarization, there could be other possibilities here. We could explore it here. Body area network. When you are putting these kind of devices near to the body here, in those cases, they try to their power, the frequency, how it is affecting our body here. Yes, what is the possibility to place those devices near to our body? And corresponding to that, what are the harms here, effect of those power on body part here, it could be find out. So the SAR evaluations here. And at the last, this is the energy harvesting part here. So what are the electromotive waves you are using for the transmission purpose? Can we again reuse them here? From some part of that energy, we can again recycle it in terms of their storage or battery or for the functioning requirement of some of the applications here in the long term. So this way we could minimize the power consumption. So this is all few of the future research problems here. Here. And these are the references which I have to consider through my presentations here. So thank you. So now the session is open for your question and answer. If you have any questions, please feel free to ask me. Any questions?
Hello.
Good morning, sir.
Good morning.
This is Rajeshwar from RCRT Chandrapur.
Okay, please.
My question is, what will happen if we change to 5G? What will happen to the IoT device? Now, we know that all the IoT devices work with the antennas for communication.
Mhm.
If we are using 2.4 gigahertz Wi-Fi, let us take the example of Wi-Fi router. If I
Mhm.
change to 5G technology,
Mhm.
whether that will impact the network communication.
Yes, this is a very good questions here. So I would like to say, and if we see from the 5G perspective here, so as we all aware here, so when you talk about 5G, then the massive antenna system people are looking forward here. The reason is so that we could improve the quality of service substantially here. So whatever the system we are using here with the single antenna systems here, now it need to be replaced with multiple antenna system here.
Yes.
By saying to go for the multiple system is a one task here, but once you go to the design perspective here, then placing a large number of antenna system at the single platform here, it's not an easy task because a lot of problem related to the integration as well as their
Yes, yes.
mutual coupling issues need to be taken care here. So those are part will be challenging challenges will be with us here, but these things will come
Yes.
because this is a job of researchers where
Yes.
we have to take care. Okay.
So maximum IoT devices available at the maximum 2.4 gigahertz right now till date.
Mhm. Mhm.
Means we are operating on 2.4. That is the maximum bandwidth.
Mhm.
But 5G needs 5 gigahertz kind of routers. So
Mhm.
the means we need to upgrade our entire IoT systems, isn't it? If we want to change the
Mhm.
basic communication from 4G to 5G
Mhm.
for better performance, that is the only solution.
No, no, just by changing the frequency is not the one aspect. See, because a lot of
Hmm.
from the hardware perspective, you have to also see that upgradation
Yes.
part here. That is just not a one frequency, there's an antenna only here. But related to
Yes.
the antenna, there are other parts, amplifier,
Yes.
oscillator,
Yes.
mixer,
Just
every,
I'm not saying
con-
that antenna is
yes,
the only thing. We have to
yes.
hardware upgradation is must.
Mhm.
So as to get the better performance from 5G, isn't it?
Correct, correct. No, no, there's no doubt in that part here, but the challenges will be related to the high frequency, how you are going to manage it. The losses, how you're going to manage it. So those
Mhm.
part will be there. So you have to find a solution for that also at the same time. How we are going
Yes.
to minimize the interferences associated. Correct.
Mhm.
So those
Yeah.
challenges will be also, but at the same time, we will have the wider bandwidth, so we can accommodate more number of services. I can accommodate more number of IoT devices.
Yeah.
So those
Yeah.
things will be there.
Yes.
Okay.
Thank you, sir. Thank you.
Okay. Thank you. Any other questions from any other participants?
Hello.
Yes, Sandeep. Please.
Yeah, sir. We know in IoT devices, miniaturized antenna will be preferred. In
Correct.
miniaturized antennas, gain will create a problem. So gain tend to be low. So how this gain is going to create gain problem is to be how it will create a problem and how this problem can be solved in context of IoT. Thank you, sir.
Okay. So whenever we talk about the miniaturizations here, the miniaturizations directly influence about the gain of the antenna. If you go through literature, you will find that the gain of the antenna gain is some sort of proportional to the dimension of the antenna structures here. the moment we are reducing the dimension of the antenna here, so some way it is going to minimize your overall gain compared to what you are getting the previously here. But in those circumstances, to enhance the gain here, you need to think of the solution which enhance your radiation here, correct? So because the gain or the directivity or all these kinds of parameters related to the radiation, the structure will be more radiating means more gains, more gain you will get it here. So other, so you can search such kind of deformation in the design or some kinds of solution which will change the path of the current here. But the same does you cannot put the slot or some other designs randomly here. It could disturb your whole surface current also here. Correct. So the placing of those things for the enhancement of the radiation will be the one part here. It will be specifically related to the your design problem we are looking here, and it is not very easy. Enhancing the gain here. Even if you try it here, you can enhance the gain slightly, but at the fundamental level, this is a trade-off. So these solutions is resolved here or resolved here with the help of MIMO antennas or the antenna array here. So if you are going for the smaller dimensions here, so if you talk about the 4G or 5G here, then the antenna arrays or MIMO is the only solutions here to move on with the miniaturizations, because through the compactness here, there will be always we lose in terms of gain and the gain here. And there are through some mechanism here, we could enhance the radiation slightly, the slightly enhancement in the gain too, not significant change in the gain will be. I hope I have clarified your answer.
Thank you, sir. Perfect, sir.
Okay.
Thanks a lot.
Okay. Thank you, Sandeep. Any other? Okay. So, any other questions? I think in the chat box. No. So there is no question in the chat box here. So with this, oh, Santosh.
Sir, sorry to disturb you again.
Yes.
This is just a general query, sir. As we have seen upgradation from 2G to 3G, 3G to 4G, there is a lot of impact on environment. And
Okay. I think.
this is because of radiation. This is just
Yes,
I'm
yes, yes.
asking in a
Okay.
general way.
No. So, Rajesh sir, I would like to stop you at this side because it's 12 a.m. So another speaker is online. He is waiting for a
Okay,
session.
okay.
So we will have another interactions here on the 5th day when we talk about the 5G antennas and variable antennas here.
Yes.
So you can keep these questions till that time.
Okay, thank you, sir. Thank you.
So
Okay.
we will have a discussion at that time here. So with
Yes,
this, I will close the sessions here, and you people can have a 2 minutes break. So after that 12
thank you, sir.
o'clock, we will start again the next second session. Okay. Thank you very
Okay.
much to you all here for being so so patient, having so much patience and listening to me. Thank you very much. Okay.